is one topic on everybody's lips: fuel. Prices are ever rising and account for more than 60% of an airline's operating expenses. Electric aircraft are in development, but their applications are very limited. Yet their benefits can be applied to certain areas of aviation. None more so than aerial agriculture. The large fluctuations in weight per mission mean that the aircraft is often burning fuel inefficiently and poses an opportunity for a hybrid. Now, there is a solution: the world's first hybrid agricultural aircraft. Designed by Aerospace Industries, this aircraft is powered by a hybrid system consisting of a turboprop and an electric motor, and offers significant fuel savings. Welcome to the new era in aerial agriculture. Welcome to Project Electric Mist.
The agricultural industry is one of the oldest in civilization, with over 40% of the land surface devoted to farming. In Australia alone, this adds to 60% of our exports and 93% of our daily food production. Based on agricultural output, the leading countries are China, the European Union, India, the United States and Brazil. It is expected that the demand for meat globally will double by 2050, and as it takes 8 pounds of grain to produce 1 pound of beef, the demand for grain will reach an unprecedented high in the near future. The current solution is to reduce the number of farms but increase their size. However, this makes ground treatments of crops difficult. This will increase pressure on aerial agriculture to become more efficient and provide cheap services. Volt Spray Industries have answered this demand by proposing a hybrid design. Our aircraft will use less fuel per mission than current aircraft, complete spray missions in a shorter time frame, while still competing on weight, hopper capacity and performance characteristics. Our main competitors are Air Tractor and Thrush Aircraft. Both companies offer a range of agricultural aircraft, each designed to suit a particular mission profile. They are sold and operated globally, and thus our aircraft will be marketed in the same manner. However, most of these aircraft have been flying since the 1990s with little improvement or redesign. A parametric study was conducted to determine what electric mist was to compete with in order to gain a foothold in the market. This revealed several problems with the current design. The first being pilot visibility. Usually the pilot sits either on or behind the wing, and this blocks his view of the ground in the spray swap, and thus he is unable to visually monitor his progress. The second was pilot load. The pilot must fly within 10 feet of the crops, manually operate the spray system, complete steep climbs and descents, execute precise turns to ensure even spraying of all the crops, constantly watch for low-lying obstacles, all the while monitoring his flight insurance. And finally, fuel. The constant climbing and descending, plus multiple takeoffs, uses an enormous amount of fuel. We also have the problem that the aircraft is underpowered at the beginning of a mission and overpowered at the end. Electric Mist aims to improve on these 3 points, as well as meet the specifications shown here. If we are to compete with current aircraft, Electric Mist must boast the following improvements: low fuel usage, which is where our hybrid design comes in, a better stall capability, a hopper capacity to spray large areas, be low maintenance, and all these improvements must remain cost effective. Our competitive edge is the hybrid design, which will reduce fuel usage and improve overall operational efficiency.
In the figure above, you can see the component location layout of our aircraft. One of the first things to notice is that unlike conventional agricultural aircraft, our hopper is located below the pilot. This allows for 2 important aspects of our configuration. The first, we can locate our hopper as near the wing quarter cord as possible, allowing for minimum CG movement during operation, resulting in minimum pitch moment inertia. The second, we can now move the pilot's position forward relative to the nose of the aircraft, compared to conventional aircraft, allowing for better forward visibility. A number of power line safety features were added to our aircraft. As you can see from the top right and bottom figure, a cutter is added to the canopy. Forward of the canopy of the aircraft, and a safety line connecting the canopy to the vertical tail of the aircraft. As well, our rudder was designed not to extend to the full span of the vertical tail, so that in case of a power line encounter, it ensures that it does not entangle with the rudder hinges.
In terms of structures, channel section spars are chosen for ease of manufacturing while providing sufficient structural support. For simplicity of design, manufacturing, the thickness of the spar cap design of the wingwood is kept constant throughout the spar length, but to optimize the weight, the flange of the spar is linearly tapered from the wingwood to the tip. Okay. Initially, a bend stiffener was chosen for piece of manufacturing, but it was later replaced with Z stiffness to allow for high moment of area while improving properties and also reducing the number of ribs. Aluminium alloys are used for wing and tail structural component, owing to their high strength, low density and corrosion resistance properties. Also, low cost, damage predictability and ease of maintenance were the chief driving factors that led to the selection of aluminium alloys over composites. So following alloys were used for corresponding components. Aluminium 2020 for T3, used for stiffness and skin, and 2020 for T81 for spars and ribs. During bending, buckling, shear flow, and torque analysis were undertaken to design the wing structures. There are 6 stiffeners equally distributed on the top and bottom skin. There are 26 ribs in our wing, 13 in each semi-span. Also note that there are 2 ribs located at the location of the landing gear, forming a small torque box for the attachment to resist the drift force. Also, the weight wing containing field runs from first rib up to 5th rib, and the spray system is supported by 3 boom hangers attached to the hard point in the wing. Similar analysis steps were taken to design the horizontal stabilizer and fin structure, the layout which is presented on the slide. A truss frame structure is chosen for fuselage. The material is chosen for high strength and corrosion resistance. To optimize the weight, tubes with different size were used depending on the loads acting on the truss members. The loads experienced by the wings are transferred through the fuselage by a pair of carry-through spars, essentially for simplicity of design, and the wing spars are attached to the central spars by double shear lock joints.
We've identified 2 missions which an agricultural aircraft would typically undertake. The first being the spray or application mission, and the second being the ferry mission. Now in the spray mission, the aircraft performs a short flight out to a field before performing a number of spraying passes, flying about 10 feet above the tops of crops. At the end of each spraying pass, the aircraft performs a short climb before performing its P-turn to descend to spray the next strip of field. The purpose of the ferry mission is to allow a contractor to fly out to a remote farm. This is done with an empty hopper, which is then refilled when the aircraft arrives at its destination. It's basically a cruise mission in which, with a range of up to 660 miles.
The goals of this project were to assess the feasibility of a hybrid agricultural aircraft. Ultimately, this assessment came down to one factor, simply being the question, is there a worthwhile benefit in a hybrid agricultural aircraft? This was assessed primarily on the basis of fuel economy and monetary savings. Comparisons were made to similar agricultural aircraft and the simulated non-hybrid form of the aircraft. Our conclusion to this question was, yes, a hybrid agricultural aircraft is both feasible and worthwhile. The benefits of this aircraft are most discernible in the ferry mission, with fuel savings of approximately 10%. The typical spray mission also saw fuel savings of approximately 4%. The nature of the hybridization was one of a split power hybrid. The key features of this system are that the propulsive power of the aircraft is divided between an electric motor and an engine. These can be run either individually or simultaneously, with the electric motor being run as either a motor or a generator, absorbing a portion of the engine's output. Shown on the slide behind me is a detailed view showing the key hybrid components, being the batteries, the motor controller, and the motor. The difficulty in any hybrid system is the storage of electrical energy, which has the obvious requirement of being rechargeable. Batteries are most suited to this application, yet unfortunately their energy density is relatively low in comparison to fuel. completing multiple charge cycles during flight, the effective energy density of the batteries increases, though even with a high cycle loading, it's still very low. Fortunately, the primary advantage of the hybrid system is not in the storage energy density, though still a contributing factor, but rather by its implementation allowing us to reduce the size of the engine. This results in the engine running at higher efficiencies for larger portions of typical missions. The engine sizing was made considering the fact that the closer the engine is sized to average mission power, the more efficiently it utilises fuel. The compromise of this is that the smaller the engine, the larger the motor, and the quantity of batteries needed. Given the power to weight ratio of the engine and the motor are very similar, the trade-off between the two is minimal. Yet a smaller engine requires larger batteries to cover the larger electrical portion of the mission, a heavy trade-off. With previous considerations in mind, an additional safety aspect was decided on. This was that the engine should be able to sustain the cruise condition at maximum takeoff weight. Combining all these considerations, the engine was sized to provide power enough to sustain the design cruise condition at maximum takeoff weight. The motor was then sized such that it could provide the aircraft's remaining power needs, essentially being the excess power required to climb. The parameters of the propulsion are reviewed and considered in greater detail. It becomes apparent that somewhere between the set engine size and an engine size and average mission power, there exists a peak overall efficiency point, ascertainable through further simulation. Essentially, this means that if you do not class sustained engine-only flight, engine-only cruise as a necessary safety feature, the engine can be downsized further to increase efficiency even further. The incorporation of hybrid hardware, though, is simply not enough. The system needs a power management scheme to monitor and control the distribution of propulsive power in the aircraft. A number of such schemes are created and simulated. The scheme of maximum benefit in its simplest description is as follows. To begin, the batteries are sized such that they store enough electrical energy to take the aircraft from a standstill on a runway, maximum takeoff weight, up to cruise altitude. This scheme is made up of two basic operating conditions. These are where the power is sourced from the electric motor, being the motor state, and where the power is absorbed by the motor, being the generator state. The power flows of these conditions are represented in the slide behind me. In the generator state, the engine is operated at maximum power, with the excess power being siphoned from the drive shaft into the batteries. In the motor state, the electric motor provides all or maximum power as required, and with any deficit being covered by the engine. In addition to these two distinct conditions, there are two blanket conditions also applied. The first is that the minimum energy levels of the batteries is defined to be a variable, the value of which is calculated using real-time altitude and weight data, used to determine the electrical energy required at that point to attain the specified cruise altitude. The second blanket condition is that if during the generator state, excess power is required beyond what the engine can cope with, the electric motor will temporarily switch state and provide the additional power until it is no longer demanded. In this scheme, the aircraft will start in generator mode. Obviously, during climb, the excess power will be supplied by the motor until the aircraft levels off, allowing the system to resume charging. When the batteries are fully charged, the switch is then made to the motor state and maintained until minimum energy level of the battery is reached. At this point, the state reverses again to generator mode, making the completion of one charge cycle. This then repeats until the completion of the missions.
In order to assess the hybrid power management scheme and determine the fuel burn in our missions, we performed a simulation of the spray and ferry missions by time-stepping the aircraft through the flight. At each time step, we'd update the weight, altitude, state of charge, and any other relevant parameters of the aircraft. We then performed a turboprop-only comparison case in order to determine whether we'd actually achieved any fuel savings. I've shown here the power distribution of the aircraft through the ferry mission, with the electric motor shown as the green dotted line and the turboprop shown in blue. You can also see the state of charge of the batteries throughout this portion of the ferry mission. Now, you can see that the electric motor cycles between charging, acting as a generator with a negative power, and the state of charge in the batteries is increasing. Once this reaches a maximum value, the electric motor switches to motor mode, and it has a positive power, and you can see that the state of charge in the batteries is decreasing. Another interesting result from our hybrid analysis is the weight of the aircraft through the ferry mission. Now you can see that there are regions with a small reduction in the weight of the aircraft. Now this results from the electric motor providing the primary power to the aircraft. Subsequently, the turboprop has been throttled down and is using very little fuel, so we have very little weight reduction in those phases of the flight. Once we had determined that it was possible to have fuel savings in with our hybrid at the design condition, we wanted to investigate whether it was possible to further improve those fuel savings by varying the hybrid parameters, namely the battery capacity and the electric motor power proportion. We found no significant trend in the fuel burn when we changed the battery capacity over the range that we considered, which was 80% to 120% of the design condition. However, we found that as you increased the proportion of power to the electric motor, it reduced the fuel burn. We reasoned that this was a result of using a smaller turboprop more frequently at its peak efficiency. We also considered the benefit of having a hybrid system in the event of a turboprop failure. Now, if this was to happen shortly after takeoff, when the aircraft was fully loaded, the electric motor would still be able to drive the prop, and it would allow you to minimize your sink speed. If this was to happen after spraying or during a ferry mission, the electric motor has enough power to sustain level flight for, in the absolute worst case, 1 minute. This gives the pilot crucial time with which to decide how best to respond to the emergency and maximize their chance of survival.
The main drive of our cockpit design was based on improving operational safety, both by reducing the pilot workload and improving crashworthiness. Behind me you can see the full feature cockpit design, the layout full feature cockpit. And you can see that we have a heads-up display, body function display, primary flight instruments, and radio and communications. So the main difference between our design and competitive aircraft design is the introduction of a multi-function display and heads-up display as standard. Unique to our aircraft being a hybrid aircraft, it's the drivetrain status indicator, which makes use of a row of LED lights to display the overall status of the system. Installed on the multi-function display are two software which are used to optimize spraying operations, with pump scan and spray view. To improve crashworthiness, we've installed a crashworthy seat which absorbs most of the impact in the event of a crash, which is also fitted with a 5-point safety harness with seatbelt airbags. To prevent the cockpit from caving in, trapping and injuring the pilot during a crash, the cockpit is reinforced with a roll cage. It's reinforced with a roll cage. And throughout our design phase, explain it in use extensively to validate our design and to compare results obtained from various analyses.
These are some of the points that we have considered. Supporting the aircraft at the farm will be a fuel bowser and swing truck, and a qualified mechanic capable of conducting light maintenance on the aircraft and fuel system, as well as assisting the pilot with refueling and refilling. In the event the aircraft will require heavy maintenance, the aircraft will be sent to the agricultural operator maintenance center. On the model, you can see the position of the hopper refilling hatch, whereas for the fuel tank, a over-the-wing refilling system will be used. The may contain corrosive material. The optimal option for corrosion protection will be a depressed current cathodic protection. This is because the hybrid is able to provide a potential difference to arrest corrosion.
Next up is the cost analysis. Even though it may seem very trivial, the cost analysis is vital with respect to project electric since one of the main aims of using a hybrid is to save fuel. This analysis was made to answer the two main questions. Number one, will the project be profitable for the manufacturer? And more importantly, will the aircraft be profitable for the operator? This analysis was based on a net present value approach with a discount rate of 10%, as this is the weighted average cost of capital in the aviation industry. To determine whether the aircraft will be profitable for the operator, first potential operating costs must be computed. So direct operating costs. A calculation of the fuel expense is shown. Estimating the number of spraying and ferry missions per year and knowing the fuel burn in these missions from the performance analysis, we can estimate the yearly fuel expense. Similarly, the yearly salary, maintenance and insurance expenses are also computed. The indirect operating costs include costs of ground facilities and equipment, as well as customer service costs, etc. Since agricultural aircraft have relatively few of these facilities, a conservative assumption is that yearly indirect will equal 50% of yearly direct operating costs. The final expense to consider is that of the hybrid system itself. Usually, engineering and development costs for future aircraft are accounted for by manufacturers by reinvesting 10% of the proceeds from aircraft sales, but we will increase this figure by 40%. This multiplier was chosen as it is the observed average increase in production costs in the automotive industry for a hybrid to be developed. In order to estimate yearly revenue, typical aerial application rates were obtained, and knowing the number of spray hours per year, the yearly revenue could also be calculated. So, for an aircraft to be profitable for the operator, the present value of revenue must outweigh the purchase price of the aircraft combined with the present value of future costs. Rearranging this, we obtain that the maximum price of electric mist is $1.5 million. At any price below that, the operator is profitable. Two things to know about that price, however. Number one, it's not a commercially competitive price. Most agricultural aircraft that are similar sell for about $800,000 in the market, US dollars. Number two, can the manufacturer even make it for that price? To answer both of these questions, the total R&D cost for the project must be calculated. This was done using the DAPCA4 method, but it was validated by putting in the parameters of a similar aircraft, the Air Tractor 802, and establishing a correction factor. For the project to be profitable for the manufacturer, the present value of aircraft sales must be greater than the total R&D cost. Once again, rearranging this, we can obtain that the minimum price of electric mist, and that will come out to be $810,000. Assuming that the manufacturer makes a 20% profit margin, the final selling price of electric mist is likely to be $972,000 or thereabouts. This number is well below the $1.5 million threshold, so the operator is likely to be profitable as well. Finally, we can estimate the fuel savings for electric mist from the hybrid. From the results of the hybrid analysis, the yearly fuel savings amounted to $19,000. That has a present value of $183,000. If this is factored in, it suggests that the effective selling price of electric mist is below that of its competitors. As such, both the manufacturer and the operator are likely to make a profit from this aircraft.
The venture of ascertaining the feasibility of a hybrid agricultural aircraft is complete. The project has been successful and the benefits determined, establishing a basis for the continued progress of Project Electric Mist. We'll now take your questions.
So the fuel benefit was mainly, he was claiming it's not very large, 4% delta. What I was interested in is that if you look at cars now, the engines that are available are probably more economical than the hybrids. So consider the fact that we will optimize this rather than this complicated system.
The problem is that it's hard to optimize an engine for the aircraft, given that its weight varies so substantially. Like its initial and final power requirements vary from like 100 to like 40-30%. So optimization of just an engine we briefly considered, but not in detail.
So obviously downtime is a big thing for the productivity of the aircraft. What's the charge time based on the batteries or IO?
We haven't looked into hot spotting, but charge time.
Well, the basic idea is that the aircraft is able to recharge the batteries when it's descending, so that when you land, your aircraft has a full charge.
That takes the inefficiencies in your day batteries.
It does, yes. Lithium polymer batteries. Yes.
I'll get closer up here. Good, thank you. If you looked at microturbine hybrid arrangements, as the microturbine battery, instead of having a motor which is capable of drive or not.
So you're talking about the series parallel setup. Sorry, the series hybrid setup. We did look into that, not specifically a microturbine, but we felt the benefits of the split power hybrid were more substantial. Basically, because the power requirements, as I said, vary so substantially, the efficiency comes from running the engine at constant power. But if we,
think what you're doing there is an accumulator or a battery.
Yes.
Which basically supplies power. And that drives the motor and the microturbine. Which is running around something like that. It's running just about all the time. But it's basically charging the battery.
But that actually doesn't give rise to any potential for energy harvesting. The only way you can harvest energy that way is throttling down the engine when the motor comes in, whereby we're actually using the excess energy.
Yes, I'm just wondering whether you've done a trade to see whether that works out.
Yeah.
Because I think like your comment made up there, a lot of these hybrid systems are showing themselves to be not necessarily working out.
I think the main disadvantage of the series hybrid for us though was that they're more suited for long range sort of aircraft with fairly constant power requirements, being that you have a micro turbine or this power supply running at a fairly constant power output. It's to do with the fact that we changed our power requirements so substantially. Its efficiency or benefits of the series hybrid is sort of lost. Yes.
You showed that you're running quite a few cycles on the battery.
Yes.
During one. Did you account for like the number of cycles there, how long the battery is going to last, how often you're going to need to replace that battery, you forward costs, because lithium batteries aren't cheap. Say, when you're talking about an aircraft that's, you're saying it's $160,000 more expensive than the nearest competitor, and you've got farmers going to have possibly replace the batteries on a
Yes. We didn't consider the cycle life of the batteries, but we did choose batteries with substantially higher cycle lives than other batteries. We specifically chose ones for this application.
which will actually be more expensive.
Yes.
That was accounted for in the cost analysis. The main reason why the increase in the automotive industry, that extra 40%, that's essentially from the re-engineering costs. So I'm not certain, but I'd say part of that would include replacing the battery.
Just there's a big difference in operating costs between your competitor aircraft as well as $1,000 cheaper than your aircraft. You say fuel, but is there a saving in the long run?
Well, the main assumptions in the cost analysis were mostly conservative. So our aircraft was designed to be sold, the project will be sold for 35 years, which is actually less than similar aircraft which have been operating since the 80s and the 90s. The manufacturer was given a very large profit margin. Normally profit margins in the aviation industry are 20%.
We had a question earlier about using piston engine. But what about using, instead of using a turbo shaft, using a heavy fuel piston engine?
I didn't consider that.
Because you would expect it to be better.
Yeah, we just did.
Because you're only getting 4%.
Yeah, that's only the spray mission though. The other thing is we were highly conservative on most of our assumptions in the hybrid system. So we expect that when you look into it in more detail, the savings will go up, not substantially, but above what we stated. And we haven't considered, the major thing we haven't considered, which is for future development, is the turbining of the propeller, which would further increase the fuel efficiency.
When you said, the only place where you get a benefit would be in rocket.
There's also ferry missions, which are long distance missions.
Nothing but that. The whole thing would be designed around ferry cruise position.
The savings on the ferry missions are 10%. They're 5%.
This is much longer. Spray missions last that.
Because in the spray mission it's riding on a different hopper, the engine is severely overpowered. So we can basically alternate between the engine on and the motor running the generator, and then the engine off, running and the motor running as a motor. And that basically in the low power conditions is where the aircraft gets a lot of efficiency.
Yeah, sort of on that point as well. You would think if you take the analogy of a car, a hybrid car, right, they sort of get your energy savings from also from the braking aspect. Right? If you're thinking about a cost emission continuing going up and down, did you consider, I guess you touched on it, harvesting some of that energy in a sense as well? Because that would really clearly take it up.
Yeah, we did look into it in detail. It was, we basically didn't get that far in hybrid. We wanted to have something complete to simulate, and that was a further addition that we were looking at, but haven't finished.
You seem to show up reference for 2024 type materials to the construction of the wing structure. What are your fittings made from? You showed the log connections at the wing transport joints. No, not the fuselage. What sort of material,
The material to connect
what sort of materials were you using for the spark caps and the transport joints? You showed log connections and log at the wing transport joint. What sort of materials were you thinking of using for that? It's a trick question in a way, because if you stick with 2024, just be aware that it's very susceptible to 2043 of use those type of things anymore. It's very susceptible to transfer and crack.
So the answer is, just say 70-50.
Yeah.
70-50. That's a good presentation too, and I like the costing, it's very good.
Thank you very much.
I think we need a couple more screens. Throwaway comment from a non-structures person, me, right? This composite must be terrible stuff because you don't like airplanes. We've seen a number of aircraft now.
We did actually consider using composites for the skin of the tail especially, but considering the environment in which these aircraft are going to be operating, you've got a lot of kick up rocks from landing on unsurfaced or unpaved runways. So composites have really low impact tolerance. So that's why we opted for metals as well. The fact that these aircraft are normally serviced at the end of the season, at the end of the crop dusting season by a mechanic. So adding composites to a hybrid would just increase the costs.
Don't agree.
Just add to that, actually, there's increasing amount of use of composites in agricultural aircraft because a lot of the chemicals involved are very corrosive, and composites are very good at that. Just a question though, what led you to put the hopper underneath when every other aircraft on the planet's got the hopper in front? Well, I've been involved in manufacturing aircraft that has a hopper underneath the pilot. It's not a very good idea. I didn't design it, but I made it right.
One of the considerations to that, when we're looking at making the hopper removable, and then we could basically extend the use of the aircraft even further, such as for using like seeding applications, not just spraying applications.
But you have, the conventional ag aircraft, or any ag aircraft, that's where they put the seeds in the hopper.
Yes.
And the interesting thing about it is the loading system you've got where it all goes down through a fairly narrow filling deck won't work with solids. Right.
The tube's actually quite large. It's about 120 millimeters in
I can
diameter.
assure you that's very small. The top of the hopper on an ag aircraft is a metre square. Right. And that's where they need to put solids and seeds. And the other thing is that these days a very large proportion of agricultural aircraft in the off-ag season they use firefighting. Right? And you need to get water into the middle, retardant into the hopper as soon as you can. So to me there's simply no real reason for the hopper underneath.
You want to show FR23 crash where you can still the battery hopper going over the pipe helmet possibilities.
Well, the batteries are quite far back, but on the hopper again, with the firefighting mission in particular, we considered that in quite a lot of detail. The hopper will take about 2.5 minutes to fill, and water anyway. And for the firefighting mission, it has another major advantage being a hybrid in that around the fire-affected areas, there's a reduced oxygen and a lot of particulate matter which can severely affect combustion engines. So the hybrid actually has a big advantage there, being that it can rely on the electric motor for substantial periods of time to get fuel.
You might find actually that a firefighting mission might support the hybrid philosophy rather than because you're operating for much shorter periods of time. But most spraying these days is fuel lease spraying, and the weight of the aircraft, as you show, decreases fairly slowly. Whereas the firefighting mission, It's, a couple of minutes, dump the load, a couple of minutes back again. And the hybrid would work very well for that because you're doing all your climbing at high weights.
Yeah, well, I mean, the design route was for an agriculture one, but we did.
Well, I think 5 weight is
Yeah, it is very well suited for that.
Would you consider what would happen if you damaged a wing out somewhere and you have to land?
We specifically didn't use the stress in structure that is more damages, but I think
A very nice feature of I'll tell you what I'm thinking of.
Yes.
A very nice feature of these airplanes is that, well, like a PA-36, you can actually put a spare wing section, outer wing section, and take it on a trailer and actually do the wing replacement out on the field, and then take off and come back to a more suitable repair place with your older damaged wing. And did you use the PA-36 for your baseline structural arrangement? No? It looks similar.
That's a good asking on that, but they've got a large cargo space and really they've got offset like outside. I'll just draw attention to the use of lithium older batteries as well.
they're a bit further behind the car, but they're encased in glass fiber. So, and they're separated into 4 sections for the safety reasons.
That is a go for its as you add it on another, I believe, reduce the size of the motor.
The reduction in the engine and the compensation by the motor, power to weight ratio of the motor is actually slightly higher than the engine. So it basically doesn't have as large an impact, but we have obviously things around
Yeah, but it's still very bad. It's just that the wing on the top is not very second. So yeah, it's stable.
Yeah, just wasn't the same.